Let's see what is centripetal acceleration. So again, let's consider a body traveling along a circle. Okay, it has a mass m. So this is the center, and it is moving at a velocity v, and the velocity direction is tangential to the circle. Now, since the direction of motion is changing, so at some point the velocity is here, at another point it would be here, so it is always changing the direction, so meaning that the velocity is changing, but the speed of the particle remain at a constant speed all the way through the motion itself. It's only the velocity is changing because it is changing direction, and acceleration is defined as the rate of change of velocity. Therefore, we say that the body is accelerating all the way around the circle. And this acceleration is called the centripetal acceleration. And this acceleration is directed toward the center of the circle. And the force, which we call the centripetal force, is also acting towards the center of the circle. And it is given by Newton's second law, which says that the force is the mass times the acceleration. And in this case, the acceleration is a centripetal acceleration. So, both are directed towards the center of a circle, as you can see. So we know that the speed of the particle is constant all the way around the circle. It is constant. Therefore, there is no change in kinetic energy of the motion, since kinetic energy is half mv squared. So no change in speed, no change in kinetic energy, and therefore there is no work done by the force. So work done by the force is zero. And as you can see, the force, which is directed towards the center, and the direction of the motion are perpendicular to each other. At each point, it is perpendicular to the motion. So the motion and the force are perpendicular to each other, and therefore work done is zero. So force and direction of motion are perpendicular to each other. Therefore, work done is zero. There's no work done. So let's see that if we can arrive to an equation for the centripetal force. We know that the centripetal force is given by the mass times acceleration, which is a centripetal acceleration. And centripetal acceleration, by definition, was v squared divided by r. So if we substitute into this equation, so the centripetal force would be m times v squared over r. So this is the formula for centripetal acceleration. And we also know that the velocity is r omega. Or omega is the angular speed. So if we substitute the velocity in this equation, it will give you m r square. So r square omega square divided by r. And this is just m r omega square. This is another formula for the centripetal acceleration. So now let's see the motion in a vertical circle. So again, let's say this is the front view of a circular motion. So this is the center of the circle, and we have attached a string to a mass. Okay, and the mass is traveling in the circle. So at some point it would be here, and at some point it would be here at the top. So let's see only 3 positions of the motion. Let's see at position A, B, and C. Let's suppose that the string has a length L, and we swirl the mass around in a vertical circle. So at position A now, we know that at this position we have the weight, which is given by mg, and the tension is upward, T. The tension is providing the centripetal force. Now we can say that at position A, since we can resolve the 2 forces, here is T and downward is the mg, so the net force is mass times acceleration. And the net force, if we resolve this, we know that the centripetal force is towards the center, and therefore the acceleration of the body should be toward the center. And therefore it is T minus mg, and this is m times the acceleration, which is the centripetal acceleration, v squared divided by r. And therefore if we want to calculate the tension, it will be the mg plus the mv squared over r. And the r is the length of the string. It is L, so we can just replace it by L. So this is at position A. We can come up with this equation. Now at position B, so the centripetal force is directed to the left and the mass is down, mg. So the only force that is providing the centripetal force is the tension. So we can say that the net force is ma, and the net force itself is a centripetal force. So it is the tension providing this, and it is T is equal to mv squared over r. R is L, so I can just write L over here. And at position C, which is the top position, so we have the tension down, and we also have the the weight of the particle mg downward. So here the mass and the weight, the weight and the tension is downward. Okay, and the net force is ma, so it is the centripetal force that is providing it, and therefore it is tension plus the weight, and this is mv squared over L. And if you want to find the tension, you can just put it as a subject. It is mv squared over L minus mg. So this would be the equation to calculate tension at position C. So if we want to plot a graph of the force and the angle, where angle would be given by theta, this theta, as the mass is moving to the top, so we can plot a graph of the force and the angular displacement. So let's consider the circle, again, the vertical circle. And here is the center. This is the length of the string L. The velocity of the particle is tangential, V. And suppose at some point the particle would be here. So it is at some angle theta. So the tension is toward the center of the circle, and therefore this mass would have a weight mg, and the tension would be here. Therefore, if we continue this line, we can say that this is also theta. Okay, so this is mg cosine of theta. Okay, because this is mg and this is the theta, so this is mg cos of theta. And we can say that the tension is T, and T is equal to mg cos of theta. So for this to be balanced, we can say that the net force is ma, and the net force would be T minus mg cosine of theta. Okay, because the centripetal force is directed toward the center, therefore the acceleration should be in this direction towards the center, and therefore it will be T minus mg cos of theta, which is equal to mv square over L. And therefore T is just mv square over L plus mg cos of theta. So if we want to plot a graph of the force against the angle theta, so let's suppose theta is 0 and we take intervals of pi by 2. So pi by 2, pi, 3 pi by 2, and 2 pi, 360 degrees, so a whole circle itself. So when theta is 0, you replace cos of 0, okay, which is just 1. So cosine of 0 is 1, and therefore this is mg, and you will have mv square over L plus mg. So this force would be mv square over L plus mg. So this is a force starting here. So halfway you will have mv square over L, and here you would have mv square over L minus mg at this point. So we start with this one when it is 0. So when theta is pi by 2, you can replace it. You will have mv square over L. So it would be here. You can just replace this by pi by 2. Cos of 90, okay, is 0, and therefore this whole term eliminates. And therefore, if we replace theta by pi, cos of pi, which is negative 1, and we will have minus mg, and therefore the curve would continue like this. So 3 pi by 2 and 2 pi, it would be a curve like this. So this is a curve of force against the angular displacement theta. So you can calculate from this, you can calculate the maximum tension, which is of course mv squared over L plus mg. You can calculate the minimum tension, which is mv squared over L minus mg, which is here at the bottom, and this is the maximum tension. This is a minimum tension, and therefore the change in the tension would be the maximum minus the minimum tension, and this would just give you 2 mg. Okay, so you have to minus these two equations, you will get 2 mg.